Y, or Z?
Y.
Y. So it's in the Y. And we want to find the moment in the X. So what's our distance have to be in? So if the Y, this is the Y, and this is the X, what's this distance have to be in? The Z. Evan, do you want to change something? What should it be? Should be 9. And now what's this amount to be? 2160. Okay, so the 240 is in the Y. We're trying to find the moment about the X. So it's, if you extend this line, it's going underneath the X, right? And the perpendicular distance is 9. So it's the absolute value of 240, absolute value of 9, and then how do you determine the distance, the direction? You put your fingers in the direction of force, the 240, palm goes towards X, and is your thumb pointing in the positive or negative X direction? The positive X direction, so it's a positive. Okay, Tara, how come the moment about the y-axis is 0? Because it's parallel. The 240-pound force is in the y direction, and it's parallel to the y-axis, so there's no moment. It's because it's parallel. Okay, how about the moment about z? David. So our force is still in the y, right? And our moment, we're looking in the z. What's this distance have to be? In the x. So let's see, 240. And the x, we're trying to find it about the z-axis, so it's got to be x, 240, about the z. And what's the x distance? 16. So my force is coming out here, 240, and I'm trying to find the spin about the z-axis. The perpendicular distance is 16. So it's an absolute value of 240 times the absolute value of 16. I put my fingers in the direction of the 240, palm towards z, and I get a positive value. A positive value. It takes practice, right? It takes practice. One part of it is to be able to see it in 3 dimensions and then figure out how it's spinning. Again, what works best, and they're all in here, are these axes. So here, let's see, we have x coming out at us. Here's x, here's y, here's z. I have the 240-pound force is going underneath the x. So it's going to create a spin like this around the x, which is positive. Then it's going under here, but it's also to the side of the z. The force is here. This is the perpendicular distance. And my fingers are going to go around and try to spin z in that direction. I don't know, you might be uncomfortable carrying around Tinker Toys, but I have smaller Tinker Toys. They're up, they're in the STEM Center, right? There's little ones, itty bitty ones that you can put in your hand and don't show anybody. But it's really helpful to help you figure it out in 3D. Or I know in graphics, Karen and I have always used Play-Doh. We have Play-Doh too, where you build a model and then you can look at how the forces are. Use whatever method you need to use to be able to do it. Jill asked me a question about the next one, because the next one's looking at the 300-pound force. We're not going to do it now, but Andrew, the 300 pounds is going in which direction? It's going in the positive x direction. So does it create a moment about the x? No. Jill, does the 300 create a moment about z? Does it cause the z-axis to spin? Is there a perpendicular distance? So the 300 is in the x, the z-axis is in the z. Is there a perpendicular distance between the 300 and the z? Yes, and it's in which direction? Let's see, the force is in the x, right? The moment's in the z, the distance is going to be in the y, and what's the number? 30. Positive or negative? Fingers in the direction of force, palm towards the, what are you going to get? Negative. And then Santiago, does the 300-pound force create a moment about the y? Take a look at where the 300 is and where the y is.
I believe it does, but there is no distance, there is no perpendicular distance.
There's no distance. So think about when you're talking about a moment about the y, you're talking about it either spinning towards you or spinning back. Can this thing spin if the force is right on it? So here's your y-axis, and here's your force. I could push it, right? But can I spin it? No, I can't. Because the force intersects that y-axis, because it intersects the y-axis, it can't cause a spin about that y-axis. Okay.
So the moment about the y is 0?
Is 0 because why?
Can't spin it.
Okay, so it's intersecting.
Yes.
Okay, so we already said back to this problem, if I have a force and it's directed at the joint, I'm not going to be able to create a moment, right? I'm only going to be able to move it translationally. This is the same situation. The 300 pounds is intersecting the y-axis. It's intersecting the y-axis, it's hitting it. There's no way it's going to be able to spin it. Only if it's above it or below it will it cause it to spin. This is going to be it's going to take time to get used to. This is just the first time we're doing it. The first time we're going to do many, many, many. Okay, so let's solve these problems vectorially now. Okay, and you're going to get it like that because you know how to do it. You know math. You have to picture the engineering part. So let's go back to a 2D problem first. Let's go back to this guy. I'm going to erase the board. Is that on the board or this is simple? Okay, so we did right-hand rule, right? What we're doing now is rather than solving for the moment using the right-hand rule, we're going to solve for it vectorially. Here we did it with the right-hand rule, so tell me, the moment is equal to what? R cross F. So in this problem, where did I want to find the moment about? Which point?
The origin?
Point O. I want to find the moment about point O. And where's the force? Is there a point there? Do they call it a point? I don't see a point label. Do you? I'm going to cut this now so you can see it better. Let's call it point B. That's point B. So we wanted to find the moment about point O due to the force B. R always has two subscripts. R goes from the point you want to find the moment about to the tail of the force. You have to be comfortable with these subscripts. I'm trying to find the moment about point O due to the force B, so my R goes from O to B. So now, what is ROB? Kyle, we're up to you. So I want to find the vector, I'm calling it R, from point O to point B. So what's the distance it goes from O to B in the X direction? 300. And what is the distance in the Y? 500. Is it millimeter? Okay, did I just write that vector correctly? Going from O to A, it goes 300 in the X and it goes 500 in the Y. And the units are millimeters. And now we want to represent the force in vectors. And the force at B, we have two forces there, right? I don't know if we ever wrote down what all the forces were. What were the X and the Y components? Let's see, let's write it over here first. So F1 is that one, it's 500 times the cosine of 45 plus the cosine of 45J. Is it Newton? Yeah, Newton or kilonewton? Kilonewton, which equals 5 times 0.7071 I plus 0.7071 J kilonewtons. And it came out to be, what's that, was 5 times 70, 71.
You got
3.5 I plus 3.5 J kilonewtons. And what did we get for F2? Let's just write it over here. F2 is equal to, it's 3 kilonewtons. And it's cosine 45 again, right? Plus, is it cosine 135? Am I doing it right? 45 would be theta x, up to theta y would be 135. So what's this come out to be? 2.1 I minus 2.1 J kilonewtons. And then I could do both checks, right? 3.5 squared plus 3.5 squared under the radical should equal 5, and it does. And 2.1 squared plus 2.1 squared under the radical equals 3, and it does. And a positive negative visual check. I should have a positive x and a negative y, I do. And positive negative visual check. They're both positives, yes. So what is the total force at FB? It's going to be the sum total of these two guys together, right? We have F1 pulling it up to the right and F2 pulling it down to the left. So that's 5.6 I. And then 1 plus 1.4 J. Does everybody agree?